on that particle. So I'll give you a minute to kind of ponder this question here. So if a chemical gradient existed, under which conditions would a particle not be transported across a membrane, even if the membrane is permeable to that particle? So I'll give you a couple seconds to kind of think about what this question is asking, and then share like some ideas you may have. So let's kind of let's rephrase the question. So if we have a chemical gradient that we know wants to move the particles from a high concentration to a low concentration, what would have to happen in this cell for us to see zero movement of the particles? What would the electrical force have to look like for there to be zero movement, even though we have a chemical gradient or a chemical driving force? Okay, so we've got some answers here. So if the electrical force is larger than the chemical force, so that's a good guess. But if we think about that, if the electrical force is larger than the chemical force, then the overall direction is going to be in the direction of the electrical force. So we're going to still see movement. What would it take for us to see zero movement? So someone else is sharing when the electrical force is equal to but opposite in the direction of the chemical force. So that is absolutely correct, okay? So if we've got a chemical gradient existing, but we see zero movement of particles, that automatically means that there's an electrical force acting that is exactly opposite and exactly equal to the chemical force. Therefore, both forces cancel out and we see zero movement of the particle in question, okay? So when the electrical force is equal to and opposite of the chemical force, then we have zero movement of the particle because both forces simply cancel out, okay? And so that's going to be really important in understanding how we have this electrochemical force that could be acting in opposite directions. So now let's speak about that equilibrium potential. So the equilibrium potential is a type of membrane potential, but it's the membrane potential specifically when the electrical and the chemical forces are equal and opposite, okay? So the equilibrium potential is the membrane potential when our forces are equal and opposite. And what that really means is the equilibrium potential is the force or the potential that wants to bring the particles to equilibrium. It's really a force that is determined by the chemical driving force. But if we have equal and opposite forces, then automatically we again have no movement because the forces have been canceled out and we're going to see zero movement across the membrane. So I'll kind of recap that here again. The equilibrium potential is a form of the membrane potential, but it only exists when the electrical force is equal and opposite to the chemical force. And so the opposing forces cancel out and we see zero movement. Another way of thinking about that is that the particles are at equilibrium. And so it's the force that wants to bring the particles to equilibrium by canceling out those two opposing forces. Okay? And when we say equilibrium, this is just a fancy way of saying that the particles are at a steady state, they're at a balanced state, they're at equal distribution. And so we don't see any movement across that membrane. Okay, that's what the word equilibrium means. That's what the equilibrium potential is. So let's look at the equilibrium potential here. Now, when we speak about equilibrium potential, we're usually referring to the potential of an ion. So whereas the membrane potential is the overall state of the cell. So let's say the membrane potential here is negative 94 millivolts. That means that the inside of the cell is negative 94 with respect to the outside of the cell. But the equilibrium potential is referencing an ion. So in this scenario, we're looking at the equilibrium potential of potassium, and that is the force where potassium does not move, the overall electrochemical driving force is equal to 0. And that is because there's an electrical force that wants to move potassium into the cell and an electrical force that wants to move potassium out of the cell. And at that potential, the equilibrium potential of potassium is equal to the membrane potential of that cell. Okay, I really want to stress that point, that we're going to have no movement because equilibrium potential is the same value as membrane potential. Another way of thinking about that is electrical force is equal and opposite to the chemical force. Okay. All right. Let me take a pause here and kind of digest that a little bit. Let's see what questions may come up about that. So far, we've talked about the electrical driving force. We've been speaking about combining the forces, and then we talked about this electrochemical, which is a sum total of the forces. And now we're really trying to figure out what is the overall movement of the particle if we take both the forces into account. Here we're speaking about the equilibrium potential, and we're talking about how that value compares to the membrane potential. Okay. So let me know what questions you have so far, and we'll try to clarify and then keep going. Okay, so excellent question coming up here. So if we have two monovalent particles, so let's say we have potassium, sodium, do they have the same amount or strength of force? So the amount of strength is going to be determined by the state of the cell, right? We said that the membrane potential along with the charge and type of particle is what is going to determine the strength of the force or the magnitude of the force. So if we're looking at potassium and sodium, if they're in the same cell, then they have the same force acting on them, okay? If we looked at potassium and chloride, they would behave differently because there are two different types of charges on them, right? One has a positive charge, one has a negative charge. So while the strength of the force will be the same, the direction of the force is going to be different. It's going to be opposite because they have two different charges. They're going to be attempting to move in two different directions, if that makes sense. Okay. Any other questions coming up so far? All right. So now we're going to determine the electrochemical driving force. So this is kind of the steps we're going to take in order to determine what is the overall direction of the particle in question. Is it going to move into the cell? Is it going to move out of the cell? And this is how we're going to walk ourselves through deciding whether or not the chemical driving force is stronger or the electrical driving force is stronger. But what I want you to bear in mind before we actually delve into this is that the electrical driving force is really determined by the membrane potential. So let's go back here. So the chemical driving force is really determining the equilibrium potential, and the electrical driving force is really determining the membrane potential. So if you can kind of associate those two variables in your mind, that is going to help us determine what is the overall movement of the particle, okay? All right. So let's kind of walk ourselves through a flow chart to decide where is this particle going to go overall if we're taking both the forces into account. So the first thing we want to do is identify the chemical driving force, and I'm gonna abbreviate that with CDF, and the electrical driving force. Direction. Okay, so the first thing we want to see is whether or not the chemical driving force and the electrical driving force are acting in the same direction. So if they are in the same direction, that's going to be easy and straightforward. We kind of talked about that example. So the first scenario here is that the chemical and electrical driving force are in the same direction. And if that is the case, then the electrochemical driving force, I'm going to abbreviate that with ECDF, the electrochemical driving force, which is the sum of the forces, is going to act in that direction, right? Easy, straightforward. Okay. Let's look at some more complicated scenarios. So let's say we've got forces in opposite directions. My arrows look terrible. Please excuse me. Okay, here we go. So now we have an EDF and a CDF, electrical and chemical driving force, acting in opposite directions. Okay. And what we're going to want to do at this point is then turn our attention to the equilibrium potential and the membrane potential. So if the forces are in opposite directions, we're then going to compare the equilibrium potential of the particle in question, so equilibrium subscript X, and the membrane potential of the cell in question. Okay. And basically, if the equilibrium potential is greater, then the overall force is going to favor the chemical driving force. If the membrane potential is greater, then the overall force is going to favor the electrical driving force. Okay. So remember I said that the equilibrium potential is determined by the chemical driving force. The membrane potential is determined by the electrical driving force. So if the equilibrium potential is a greater value, that means that there's a stronger chemical driving force and the overall direction is going to favor the chemical driving force. If the membrane potential is a stronger value, that means that the electrical driving force is a greater force. And so the overall movement of the particle is going to favor the movement of the electrical driving force. Okay. So let's go through some scenarios here to apply that. Okay. So the first scenario is if equilibrium potential is greater than membrane potential, then chemical driving force is also greater than electrical driving force. And so the overall ECDF, the combination of those forces, is going to follow or favor the chemical driving force. So the electrochemical driving force favors the chemical driving force. Okay. The second scenario is if they're equal, right? Let's say they're in opposite direction, but they're equal. And we talked about that here a while ago. So if the equilibrium potential is equal to the membrane potential, then we have the CDF, or chemical driving force, being equal to the EDF, or the electrical driving force. And therefore, the electrochemical driving force is going to be 0. Remember, it's going to cancel out. Both of these forces cancel out if they're opposite, but they're also equal. And then here we say that the ions are at equilibrium, so there's no net movement. And we saw this in that scenario that we looked at where the equilibrium potential was -94, the membrane potential was also -94, and the particles were at halt, right? 0 ECDF, no movement because those forces cancel out. And then the final scenario here we'll wrap up with is if they're equal and opposite, but the membrane potential is greater than the equilibrium potential. So if the membrane potential is greater than equilibrium potential, then here the electrical driving force is greater than the chemical driving force. And so if we look at the overall ECDF, or the combined forces, will favor the electrical driving force, okay? So this is how we determine the overall direction of the force when we combine both parts of the equation, so both electrical and chemical forces, and then we figure out based upon the direction of each of those forces and then the value of the membrane potential and equilibrium potential, whether or not the particle is going to favor the chemical driving force or whether or not the movement of the particle will favor the electrical driving force, okay?